Okay, cool. So welcome to the electrical overview for Mark 6. Super excited to see everyone in here. Hopefully you learn a thing or two. So first off, what to expect in this presentation. So we're going to be looking at all of the high-level systems that make up Mark 6 and let it drive forward. We will, for the most part, not look at any PCB schematics or layouts. We will not be assuming any prior knowledge of FSAE or of electric cars. But if you have an ISIM level of EE knowledge, that can be helpful. It is not required, though, by any means. Now, unfortunately, despite my best efforts, you will not be an expert in every single board on Mark 5 or Mark 6, sorry, after this presentation. But the goal is that you will understand how all of the different building blocks fit together and what purpose they play in creating a working car, even if you might not be able to describe how each one of those building blocks are built. So with all that stuff out of the way, this is the Mark 6 block diagram. So this shows pretty much every critical system that we have on Mark 6. And I'm sure that if you stared at this for long enough, you'd eventually learn how Mark 6 works. But that's not why you're here, and that's not why I'm here. So let's break it down. So all of these different, images. Actually, let's see if I can turn on a laser pointer. That might be helpful. Perfect. Can y'all see the little laser pointer now?
Yep.
Yeah, so all of these different, we got resistors here, relays, we got boards everywhere. So those are all our elements on the car. And then the colored lines are the different ways that they are connected. So these red ones are what's called the GLV system, the grounded low voltage system. So this is coming from our two low voltage batteries down here. And they provide power to pretty much all of the low voltage boards on the car. Next up, we've got CAN. So CAN is these green lines here. If you don't know what CAN is essentially the language that our boards are speaking when they talk to each other. It's the primary way all of the boards on our car are communicating and passing information back and forth. I'm not going to get too much into how CAN works, but I think it's pretty artfully summed up over here. Basically, we use CAN on our car because it does a very good job of taking care of our data and making sure that it gets to its destination without being corrupted, as you can see here. Next thing, we've got these blue lines, which indicate the shutdown circuit. So I'll get all into what the shutdown circuit does, but for now, what you need to know is the shutdown circuit is how we turn off the car if something bad is happening, right? There's an unsafe condition somewhere. We activate the shutdown circuit and we turn off the car. And lastly, everything in orange is our high voltage stuff. So this is really sort of the heart of an electric vehicle. And this is how you get power from your accumulator to your motor controller to your motor, which lets you spin your wheels around. Cool. So let's get moving over here. So if you're looking at, someone who's driving around our car, right? What do you see? They put their foot on the pedal and the car moves. And we're going to take that chain of events and sort of break it up a little bit into these different stages. So we've got our actual throttle pedal over here, right? And then we've got our throttle board. So this is passing some information to our throttle board. Our throttle board is also receiving information over CAN. So I use these green arrows from two different places. So it's receiving information from the brakes and it's receiving information from the dashboard. Based on these two things, throttle message will send its own CAN messages to the motor controller. And the motor controller inside of this CAN message is what's called a torque request. So we're telling the motor controller, hey, I want this much torque from the motor. This is how much I want the motor controller or the motor to spin. And the motor controller does all kinds of fancy calculations. And based on the amount of torque that you're requesting from the motor, it draws the perfect amount of current from our battery, which is these orange bits, high voltage from our battery, to make the motor spin that exact amount. And then, of course, the motor is connected to our wheels, and that's how we move forward. So I'm going to take each one of these links and break down exactly how it works. And hopefully by the end of that, you'll know exactly what we need in order to make a driving FSAE car. So first up is a throttle pedal. So if you look right here, you can actually see them in this CAD diagram. But this guy right here, and there's another one behind there, are called linear potentiometers, and they look a little bit like this. And this is how we're actually able to tell how much we pushed the throttle pedal. So a potentiometer is essentially a resistor that you can vary the resistance of. So in this case, it's done by sliding this piece in and out. And you can see that right here, right? If we push the pedal in, this piece will slide down. If we let the pedal go, it'll slide out. And so I'm going to draw a very, very simple circuit diagram of what something like that would look like. It's going to look like, whoops, there you go. It's going to look like this. So you can see we have power on one side, we have our potentiometers, and we have ground. There's also these two scaling resistors. And these, I'll explain why we have these in a second. For now, what I will say is that we usually use a 0 ohm resistor for one of these scalers. And as you know, a 0 ohm resistor is equivalent to a wire. So I'm just going to make that change real quick. Perfect. So now we've got our two potentiometers, one with just goes 5 volts on one end, ground on the other, one with this other little scaling resistor in the middle, right? So if you think about our resistor divider equation, right? So voltage divider, resistor dividers, when you have two resistors and some voltage gets dropped over each one and you take out some value in the middle, right? We have V out equals V in times R2 over R1 plus R2. So if we go back to our diagram, right? In this case, our R scale is our R1, and pretend this is your other R scale. And your potentiometer would be your R2. So if you think of this as like a Y equals MX plus B linear line with this term over here being your slope, you can see that by changing R1, we're just changing the slope of that line based on, if your input is how much you've moved the potentiometer and your output is what you get out of the whole system, changing your R1 is going to change the slope. And you can see that right here. So if we have pedal travel on the x-axis and voltage on the y-axis, you can see that we have two different transfer functions is really what these are called for one of our throttle potentiometers and the other throttle potentiometer with a different scaling resistor. Now, what happens then is the throttle board then gets those two measurements and it does a little bit of math to undo this scaling on one of the resistors. So you've just got one reading that matches up from both of our pedals. And right now you might be thinking, okay, well, why do we want to do that? You went through all this trouble, you added this resistor, you didn't add this resistor, you had to do all this math to undo it. And the reason why is because of safety. So if you think about this, right? Imagine what would happen if, say, both of our potentiometers got shorted to 5 volts, right? That could mean that potentially like the car thinks that we're pressing the throttle 100%, even if we're not touching it. That's a very unsafe condition, right, to be in for both the driver and the people around the car. Or I don't know, what's another failure mode? Or the two potentiometers are shorted to each other, right? So then they would always show up as the same value. And then imagine if one of them breaks. Same situation, right? You could end up with an inaccurate sort of throttle reading. And if you didn't have these two different transfer functions, and then undo that little scaling, you couldn't tell if some external source essentially was messing with them, but with some bad connection, some short or something. So that's the reason why we're doing this whole adding resistors and then undoing the scaling. Also, the rules say we have to. So this is rule T.4.2.4, and it's basically telling us that if your two pedal value readings are more than 10% apart, that is defined as like a throttle implausibility, and you're not allowed to move forward if you have that on your car. And the scaling is a good way to check that. Cool. So we're at our first little quiz here. I'm gonna try and add in a Zoom poll for this, but this is also a great time for you to jump in and ask me some questions. You can do that in the chat. I can see that over here, or you can also just unmute yourself and fire away.
Amit, can you hear me?
Yes.
What other failure modes do we like consider in a throttle beyond shorting? Like, this is protect against.
It's a great question.
I mean, I guess, yeah.
So the throttle board has actually 3 of these implausibilities. And you know, hold on, I don't really know how these Zoom polls work. So if you want to just chuck your answer in the chat, that works totally fine. So yeah, there's 3 different implausibility modes that we're checking for. One of them is called an out of range implausibility. So our potentiometers will usually give us a value not at the extremes, right? Usually, you know, maybe between 0.5 and 4.5 volts or something. So we have a check that's saying, hey, is this value really, really low, or is this value really, really high? Like 0 volts or 5 volts pretty much. And that's basically checking, because if we have that value, that means that like, this is probably not coming from our potentiometer. There's probably a short somewhere, you know, the line is either shorted to ground, shorted to 5 volts, or something like that. So that's called an out of range implausibility. Yeah, the other 2 is the deviation implausibility that we talked about here. And then there's one more implausibility that I'm actually going to get to in the next set of slides. So I'll leave it as a surprise. Here's the polls. Perfect. There you go. Can y'all see that poll?
I think your slides.
Sorry?
I think your slides might be delayed.
What is it showing?
Now the quiz showed up.
Oh wow, that's very
might have just been for me though.
Okay, I just launched the poll. Let me know if y'all can see it. If not, I'll just not make any more.
Is there a way to open the poll back up after you've closed it? Because I had to look at the slides. I'm on phone right now.
Sorry, can you repeat that one more time?
I closed the poll. How do I reopen it? I just had to look at the slides to see what the answers were.
Oh, I'm gonna be honest, I really don't know how it works on your end with the polls. Don't worry about it.
Got it. Okay.
All right, cool. Everyone who's answered so far has gotten it correct. So feel we can move on. If you have any questions on any further point, by the way, always feel free to drop them in the chat or just unmute yourself and speak up. All right, cool. So next, there are two other, we noticed there are two other boards that are sending information to the throttle, the dashboard and the brakes. So we're going to look at right now what the dashboard is sending over to the throttle. So if you think about getting into like a regular car, right? You can't just like get in, hit the pedal and start driving, right? You need to turn the car on, basically. And the Formula car has something very, very similar. And we have something called the ready to drive checklist. So this is, if you look at these requirements, this is basically the equivalent of hitting the on button in your car or my car. So in order to become ready to drive, we have to be pressing the brakes. You have to be pressing the start button, which is a little button you can hit on the dashboard. So those two should be pretty familiar. The last one right here is tractive system must be active. So later on in this presentation, I'll define exactly what a tractive system is. But for now, you can just think of it as high voltage. So that means in order to be able to drive, right, brakes will be pressed, start button's got to be pressed, and high voltage essentially has to be active, right? We got to be able to have the high voltage so we can actually move forward. Otherwise, we're not ready to drive. So the dashboard is basically always checking, are we meeting these three conditions? Are we meeting these three conditions? Like a checklist, right? So let's say, okay, now we've met those three conditions. So the dashboard knows, okay, right? We met our three conditions, we're ready to drive. And then it sends a CAN message over to the throttle. And the CAN message says, okay, everything's good to go, we're ready to drive. And the throttle board eventually will get that CAN message. And it goes, okay, everything's ready to drive. And then once the throttle board gets the CAN message that everything is ready to go, that's the point where it's able to start requesting that torque and making the car move forward. Cool, so that was the dashboard. Next thing we've got is the brakes going over to the throttle. So if we think about the brakes versus the throttle, right? If the brakes are being pushed and the throttle is being pushed, which one is more important? Which one should we listen to? 99 times out of 100, it's going to be the brakes. Usually if you're trying to stop, probably for a good reason. And that means if you're pushing the brakes, at no point should the car also be trying to move forward, right? That would be bad. Also, this is rules required, that you can't be hitting the brakes and moving forward at the same time. And Rowan, this is the third form of implausibility. So the throttle board is also constantly checking, essentially, if the brakes are being pressed. And it's doing that because the brakes are always telling it over a CAN message if the brakes are being pressed. And if the brakes are being pressed, let's say if we hit the throttle pedal and we hit the brakes at the same time, the car is actually not allowed to move forward until you fully lift off the brake and fully lift off of the throttle pedal. And once you do that, then you can hit the throttle pedal again and start moving.
Wait, do we have another potentiometer on the brake pedal? Because I know we have
No,
the box,
so no. So the bots is something different. The way we can
Right.
tell whether the brake is being pressed is we have a pressure sensor in the brake line. So we're actually measuring the pressure of the brake line.
Okay, cool.
And
then you
there's
could like
just,
check for leaks probably.
sorry?
You could like check for pressure leaks, like if the brake pressure is like not there anymore, for example.
You probably could do that using the sensor actually. But the way we do that is with the bots that we'll get to in a little bit.
Oh, okay, fair enough. Yeah. All right, cool then.
Yeah. So here's another quiz. What are the 3 checks that we need in order to enter ready to drive? I'll get my poll up here. Oh, I don't know. I don't think I can do free response here. All right, throw them in the chat then. It's also going to be my water brakes. Yep, everyone looks correct so far. I don't have any questions about what we've gone over to this point. Those slides still working okay over that last chunk? Great. Give it another 30 seconds or so. All right, perfect. So yeah, everyone who's answered has gotten it correct. So now let's move on to the next little link in our chart here, and that is the throttle going to the motor controller. So what happens is on the throttle board, you're looking at how much the pedal is pressed. We check for all those 3 different implausibility cases. And assuming, we're all good, everything's good to go, the dashboard has told us we're ready to drive, we're not hitting the brakes, the throttle sends a torque request to the motor controller, and that's in Newton meters. And as I mentioned before, the motor controller takes our torque request and draws exactly the right amount of current so that the motor can spin at exactly the right amount of torque that we specified. But there's this like HV part, right? The motor is getting its high voltage, and we got to figure out where that high voltage is coming from exactly. And it turns out it's a little bit more in depth than just like connecting the plus side of our accumulator to the motor controller and the minus side to the minus side. There's a little bit that goes into it. So the question we're trying to answer here, yeah, as I drew yours, how do we get our power from our segment over to our motor? And this is, by the way, the actual motor that we use on the car. Not our actual, it's a stock photo of the same motor. And so to analyze that, let's rewind all the way back to the start to our block diagram. So as I mentioned, right, these red wires indicate the grounded low voltage system. This is a system that's providing power to all of our low voltage safety systems and things like that. And I also mentioned this thing called the shutdown circuit. And how the shutdown circuit's job is to turn off the car if anything bad is happening. So we're going to get into exactly how the shutdown circuit works right here. And the first thing to note is this diagram is actually not a very accurate representation of the shutdown circuit. And I just did that to make this diagram a little bit easier to make. But I'll show you exactly why this is not accurate using the T. So this right here is a picture of the red line of the T. You might have taken it. It's known for being significantly faster than the green line of the T, which is just absolutely horrible. But if you can imagine there's a train up here and it's trying to get down here or down here, it's got to pass through every single one of these stops, right, to get there. And if any one of these stops is broken, say, Kendall MIT is broken, no trains can pass through here, that means our train can't get from up here all the way to down here. And if you can understand that, you basically know how the whole shutdown circuit works. So I'm going to change a few things about this diagram and make it blue to match our block diagram. I'm going to add in a little destination and a source. So instead of a train, we've got our battery at the top of this, and it's trying to send 12 volts nominally down to our 2 destinations. And in this case, our destinations are air plus and air minus that I'll collectively just refer to as the airs. And I'll get into exactly what they do in a second. But one more change we're going to make if we're going to be really accurate. The last stop on our little train is actually before the split off point. Like there's no stops that are specific to air plus or specific to air minus. I don't know what this thing is. Someone knows trains better than I do. Feel free to speak up, but that's like not a stop for the purposes of this explanation. Cool. So we've looked at the T version of our shutdown circuit diagram. Now I'm going to show you the actual version of our shutdown circuit diagram, and it looks like this. And I know this can look a little bit intimidating, but it's really just the same thing as this, right? Here's our battery up top. There's our battery. And here are two errors down here. And we'll just take this whole path with all of these stops in the middle. Oh, there you go. So here's our battery, here's our errors, and you just take our whole path with all the stops in the middle, just like our T diagram. I'm going to hide these two little bits over here, just because they're not super relevant right now. So I'm going to go through all of these stops in order. But real quickly, I am going to define what an error is. So an error stands for an accumulator isolation relay. And if you don't know what a relay is, it's basically like a big fancy switch. And you can sort of think of the errors as the gatekeepers of high voltage. And the reason for that is because we have one error on each side of our accumulator, of our battery pack. So that's why air plus is on the plus side of the battery pack, air minus is on the minus side. And they're basically right in that high current path that's exiting the accumulator, which means that they cannot, sorry, lost my train of thought. High voltage cannot exit the accumulator if those errors are open, right? If the switch is open, nothing can go through it. The switch is closed, that's when we allow the current to flow. And as you can see here, these errors are ultimately powered by the GLV battery through the shutdown circuit. So that means the power's got to make it all the way through, and then it gets to the errors, and that's what allows them to close, right? So if we got a problem, one of these nodes will be open. All of a sudden, the power cannot get over here, and so the errors are not able to close. Errors not able to close, high voltage can't exit the accumulator. So we got another quick quiz here. Pull up. Cool. All right, feel free to fire away with questions as well.
I think we can't see the options for some reason. I
Can't
think it's
see-
something with the slides are like, oh, there's a little bit delayed, but they're here now.
Okay. Yeah, if the slides are ever like not matching what I'm talking about, feel free to, yeah, say something, because that would not be ideal. Cool. Okay, so it looks like most people got this right. So the correct answer here is A. The errors cannot open. Or sorry, the errors cannot close. And so if we go back to our little circuit diagram here, if we open the shutdown circuit, if we open one of these nodes, let's say a driver E-stop, that's open. That means our train, our power, can't get from our battery all the way down to our relays. And so this is this relay is like open when there's no power, and it's closed when we power it. And so if we can't get power over here, that means that they cannot close. Does that make sense? Cool. Okay. So now we're going to move on to the next section, which is just a very quick crash course of the shutdown circuit nodes. So all those nodes that we saw. Just as like a quick disclaimer, I'm not going to go through every single node, nor am I going to go through them in the exact order that they're wired on in the car. And that's just for convenience of like grouping similar nodes together. Cool. So first stop, we've got the master switches. So these you can think of as like the car keys on our car, if you've ever seen them hanging off the side. This is a picture of Mark V. The arrow is pointing at them. They're very, very small, but they're in the same place on Mark VI. There are two master switches. There's the GLV-MS, grounded low voltage master switch, and TSMS, tractive system master switch. And those basically do exactly what you think they would do. They either turn on the grounded low voltage system or they turn on the tractive system. And in the case of the tractive system master switch, it's actually also a node on the shutdown circuit. So it just works like any other node. And that means, oh, how about now?
Yeah,
Okay, it
they're
seems to
updated
not
now.
like it when I switch slides in my presenter view. So I'll just stop doing that. There you go. So can y'all see the TSMS? So here are the two master switches. They're really quite small in this little picture. But as I said, yeah, ground low voltage tractive system. The tractive system is a node on the shutdown circuit like anything else. So the way it turns it on is essentially just by switching over and allowing the shutdown circuit to flow through it and get all the way down to the airs. Cool. So those are our master switches. We also have 3 emergency stops on the car. So we've got one over here, which you can see is this red button. We've got another one that's on the other side of the car, pretty much in the same spot. And we've got one little one up here that's just barely visible that the driver can push. So 3 emergency stops. You hit any of them, you'll open the shutdown circuit. Cool. Next, we've got the brake over travel switch, or BOTS. And as we alluded to earlier, the BOTS is how we can tell if we've lost pressure in the brake lines. And so the way that that works is the BOTS is literally a little switch, looks just like this, you know, like any other light switch or something like that. And essentially, we stick it, nestle it all the way in here inside the brake pedal. The way that works is if you think about like the brakes in your car, right? It's kind of really easy to push for a little bit, and then it gets super hard to push as the pressure goes up. Like you can't really just floor the brakes the same way you can like floor your throttle pedal, if that makes sense. And the reason why is because of the pressure in the brake line. However, let's say we were all of a sudden to lose that pressure, there's a leak somewhere or something like that, you'd be able to push the brake pedal a lot further than you'd normally be able to, right? And that's bad because if we lose that pressure, all of a sudden we hit the brake pedal and our brake, what is it, the calipers, they can't close because there's no pressure. We can't stop when we want to. So that is obviously not a condition that we want to be driving around in. And so what the spots will do is we put it up right behind the brake pedal. And if the brake pedal goes far enough, like further than it normally would in operation, we'll actually hit this little switch and that will open the shutdown circuit and stop the car. I also just want to note that this is a picture of Mark V. I'm just going to try and call out whenever I use something that's not from this year. Cool, so that's the BOTS. Next up, we've got the inertia switch. This is my personal favorite node on the shutdown circuit, just because the little piece is so fun to play with. So the inertia switch, also known as a crash sensor, is a switch that we mount onto the chassis. And basically, it's got a little ball bearing and a receptacle. And whenever the car stops very suddenly, such as, you know, in a crash, somehow, I'm not really sure of the internals, but the ball will like get flung out of its housing, and that will open the circuit. So if we crash, we want the car to stop, more or less. Cool. Next up, we've got the brake system plausibility device, so known as the BSPD. This is one of the slightly more complicated nodes, similar to the block diagram. I'm sure if you stared at this circuit for long enough, you'd understand it. That's really boring, so I'm going to explain it with a graph instead. So I'm going to be graphing here time versus output voltage. I'm going to put a bunch of different stuff on here. The first one we're going to put is the output of something called the BSPD current sensor. Essentially, what this is telling us is how much is there current flowing to the motor, right? So let's say at this time, you know, t equals 1. Bam, right here, we got current flowing to the motor. Next thing we'll throw on here is, let's say it's later time, we're hitting the brakes. So yeah, we call this signal the brake gate. So over here, right? Over here, current's flowing. Over here, we're pressing the brakes. Now, let's think about for a second what's happening at like this point right here, right? So if both of these things are high, that means that there's current flowing to the motor and we're pressing the brakes at the same time. And that is not a very safe state to be in, because if we're pressing the brakes, again, we're trying to stop, right? But if current's flowing to the motor, that means we're like spinning the motor. We're trying to go forward. And what does that mean? That means the driver is not in control, right? That means that the driver is hitting the brakes and the motor is still trying to spin. That is, again, very unsafe for both people in the car and out of the car. And if we hold this state where we are both trying to spin the motor and we're hitting the brakes for over half a second, the BSPD board has this relay on it, the BSPD relay, which again is like a switch that's directly on the shutdown circuit. It's in that train track. And if it senses that that condition has been held for half a second, it'll open that. It'll open that relay and shut down the car. And you can see right here. So this is that BSPD circuit in board form. Yeah.
Can I quickly ask a question?
Yes, go for it.
Is the shutdown circuit like software based, or is it actually like a physical chain of switches and and it has like a wire going between all the boards?
That's a great question. It's hardware. So
Okay.
yeah, there is literally a wire that goes all around the car, stops at all the different nodes, and ends at the ears. It is physical. Yes. Great question.
And let's see, my other question. I forgot it. I'll think of it
All right.
later.
Think about it. Feel free to jump in. Okay, and then got another quiz here. Yes, I believe that was in fact when Sarah came over. Sarah is one of the Blue Origin recruiters that tends to work closely with Olin.
Oh, yeah, my other question was, so you saying like if the motor controller is getting or has current, but we're pressing brakes, this is already after the throttle board is doing the check of like our throttle board already does a check where it's saying, is the brake being pressed? Am I sending a torque request, right?
Yes.
This is like in addition to that.
Yeah, you can. Yeah, exactly.
Okay.
So this is almost like double checking that result. And so yeah, the difference is also like this opens up the shutdown circuit,
Okay.
which is like a more fatal failure mode.
Sure.
The throttle board does not actually do that. Throttle board just
I see.
says, okay, if the brakes are being pressed, just don't request it.
Oh, I see. Gotcha. Okay. That makes sense.
And the other difference between these two is the BSPD is entirely hardware based. So that's how we have that super complicated circuit. And the reason for that is because FSAE tends to like all of the safety critical stuff to be hardware only. because it's a lot easier for them to check if you've built it right. On the throttle
Mhm.
end, that check just happens in the code. In the code, we check, okay, are we hitting
Okay.
brakes or not?
Gotcha. Is the current, like the motor controller current, is that like a software signal though, or are you actually measuring current like with an actual?
No, yeah,
remember?
the current sensor is, I believe, tied to an actual current sensor in the service section, and that wire just comes all the way up to the BSPD board, the brake
Wow.
board.
Okay, it's crazy. Cool.
Cool. So I'm realizing now that I wrote this question really badly. So the way I intended this was when I said, what is the BSPD checking for? I intended this to be like the actual brake system plausibility device, but as people have rightfully called me out on in the answers, BSPD can also refer to the actual entire brakes board. And the brake system pressure is actually being read on that board. So if you answered B, that's probably also correct. This exact reason is why I'm trying to get us to stop calling it the BSPD board and start calling it just the brakes board instead, because it also does things like obviously like read the brake system pressure and control the brake light, some other things. Cool. Next stop on the shutdown circuit, we've got the tractive system connectors. So there are basically three high voltage connectors that come out of the accumulator. There is the MPC, or the main pack connector. This is like the primary high current path. This is what goes out to the motor, basically. Then we've got the HVD, or the high voltage disconnect. So this is a safety thing. And essentially it's a control, it's a plug in the back of the accumulator, and the power comes out and goes right back in, with the purpose being that if you disconnect that, you're breaking the circuit. And the reason that's there is because essentially, if there's like a crash or otherwise like medical personnel have to respond to the track, first thing they'll do, they go to the back of your car, they pull out the big orange thing, and they are confident that there's no high voltage, essentially. So if you were around for Mark 5, it was like the propeller looking thing on the back. For Mark 6, it's just like a big chunky connector on the back of the accumulator. Last, we have the TSMP, or tractive system measuring point. So if you ever looked next to the master switches on the side of the car and you've seen these like two sets of holes, those are the tractive system measuring points. And they're essentially points where we can stick in a multimeter and check what's the voltage of our high voltage system. And they've got like resistors in line with that to make sure that it's safe. Now, if you don't understand the purpose of those three connectors, that's okay. The big point I'm trying to get across is all these connectors have something called an interlock in them. And an interlock is essentially a mechanism that lets us tell if we've connected this connector correctly. And those interlocks are all on the shutdown circuit. So that means that if we haven't connected one of these three things properly, the shutdown circuit will be open at that spot. And then power can't get down to the airs to turn on high voltage. So there's one interlock for all three of these, and they're checking if we're connecting the connector all the way or like properly.
So is the interlock on the like the measuring holes, what are those called? TSMPs.
So
is that
the
interlock like inverted or something?
the interlock is like on the accumulator side, like in that
Right.
connection. Yeah.
But for the TSMP, like I'm assuming that it's inverted so that you're not probing when it's high voltage. Or wait, what? How does it? Why is there interlock on the TSMP?
There's an
That means
interlock.
you have to have something. You have to have something plugged into the car for it to like yeah.
So there's there's the TSMP signals, right? A plus and a minus exiting the accumulator at some point.
Yeah.
And so that point where it exits the accumulator, there's a little connector there. And that is the point that has to be interlocked. because if something's not connected properly, you could have arcing, you could have like potential high voltage contacts like sitting there being exposed. So that's why you want to check that those are connected. Does that answer your question?
Yeah.
You sure?
Yeah, I was thinking about it the wrong way. Like, obviously the high voltage needs to be, like, the errors need to be closed to read like the high voltage on a multimeter, for example. I was somehow thinking that the interlock was like checking if you have a multimeter plugged into the car, but I see now that you're just saying it's at like the actual place where the TSMP is like tapping power off the second or the accumulator.
Yeah, it's at the point where the TSMP signal is exiting the accumulator, essentially.
Gotcha. Yeah. Cool.
Yeah. Cool. Okay, next up is the insulation monitoring device, or the IMD. We'll try and speed up a little bit because we're not running a little bit behind. So the IMD is checking for a loss of isolation between our high voltage and our low voltage systems. So the TSMS and the GLV, not the TSMS, the TS and the GLV systems are supposed to be what's called galvanically isolated, which basically means like electrically isolated. They can't be connected at all. And I'm going to jump on my safety soapbox real quick, tell you why that would be an absolutely horrible thing. Our GLV system, the ground is actually connected to our chassis. Right? The ground is connected to our chassis. So imagine if like our 400 volt system got shorted to that, right? Now our whole chassis is energized with 400 volts. And to give you just a quick idea of what that might look like, this chart here shows resistance from hand to hand, right? So at these different voltages and at these are like percentiles of the population. So if we do a little bit of napkin math here, 220 volts is the closest to our battery pack voltage, which is 400 volts. So really your resistance would be even lower than this. And let's say you're just like an absolute resistance god and you have 2100 ohms of resistance over your hands. You were to touch that chassis while it's energized with both hands, you've now completed a circuit, right? The current can flow through you. So using Ohm's law, right? V equals IR. If our pack voltage is 400 volts and you have 2000 roughly volts of resistance, that's 188 milliamps of current flowing through your body. But if your hands were wet or you had a cut on your skin or something like that, what actually happens is the path of least resistance is now basically skipping over your skin, which is the most resistant part of you, and goes straight through your internal body resistance. And that's only 300 ohms. So again, if you got a cut on your skin or something like that, and you happen to have that circuit complete across you, that would be 1.3 amps of current. And if we look at this chart here, if you have 1.3 amps of current flowing through you at any point, you could get very, very hurt. That's what all this red stuff means over here. And you might be thinking, okay, well, 188 milliamps, that's around here somewhere. It's perceptible, but no muscle reaction. That doesn't seem that bad. But if you look at this graph here, this is telling us that this is the effects of what's happening when your current passes from your left hand to your feet. It actually takes about 20 milliamps flowing through your heart to stop it entirely. And the reason I'm telling you all this is not to like scare you, or well, it is to scare you, but not to like scare you into leaving the team or something. It's just to drive home that the stuff that we work with on this team can really be dangerous. And so when we take all these safety checks, it's for a very good reason. Cool. Another very critical system that we have is our BMS, which you can sort of think of as a battery babysitter. So if you look at this chart that Melissa made, you can see that if we have temperature versus voltage, there's this very, very tiny bit of space where our battery cells are actually safe to operate. And it's actually really even a little smaller than this because the rules cap us at 60 degrees Celsius for battery temperature. And everything outside of that is super, super bad. Bad things happen. You don't want any of these things to happen. And so to make sure that doesn't happen, we have a BMS. And a BMS is a system that Melissa designed built from these three boards that are essentially always checking to make sure that we're in a safe temperature range and a safe voltage range. And if we're ever not in a safe voltage temperature range, they also have a relay on them that'll shut down the car. Cool. So that's the battery management system. Last stop, right? Been through everything. Now we're at the airs. And if you remember, the airs are those gatekeepers, right? One on each end that control whether or not high voltage can leave the accumulator. So let's take a quick step back. The shutdown circuit provides power to close the airs. And the shutdown circuit has to pass every single one of those nodes, every single one of those T-stops before it can actually drive the airs. High voltage can't exit the accumulator until the airs are closed. And if there's no high voltage, the motor can't get any power. So what does that mean, right? This boils down to we can't drive unless we pass every single one of those checks. All right, and now we've got one more quick quiz here, which I think I'm going to, oh, I accidentally exited this. I probably won't set up a poll just to save time, but I would encourage you to think about the answer, and I'll pause for a few minutes for questions. It's a great question. So the way that the IMD checks for a loss, for the sake of the recording. So we got a question saying, how is a loss of isolation measured in the IMD? Yeah, so that's a really good question. The IMD is essentially programmed with a certain resistance value that there's a way to calculate what it should be, but it's escaping my mind right now. But what the IMD does is it essentially checks for the resistance between the high voltage and the low voltage systems. And if it's below that preset value, then it determines, okay, we've lost isolation here. And if you think about it, like if you have two things that are like not connected at all, their resistance will be like super high, like basically infinite almost. And if you have two things that are shorted together, their resistance will be very, very low. So that's how the IMD checks for that. And the IMD is actually a part that we like buy off the shelf. And it has to be programmed to like a specific resistance value. Does that answer your question? Dope.
What does the IMD like physically connect to on the car? Does it have like a lead that connects to the chassis and the accumulator, or how does it work?
You know what? I'm not actually sure exactly which points on GLV and track system the IMD connects to. That is a great question, though. I can try and find out.
But it does.
Too.
It does connect to both. Is that true?
I believe it has to. Yeah, I'm just not sure where.
It is physically in the service section.
Okay.
Yeah. The board that communicates with it is the IMD latch, which is on the service section motherboard in there. So up in the lid.
Cool. Let's move on here. So great, right? We got a throttle board. It's got all its checks, right? We got HV. We're all good to go. Let's drive. So we got our startup checks. Yeah, as I mentioned, right? TS is active. And this is the point where I'll actually like very formally define tractive system. Tractive system is the high voltage past the airs. So once the airs are closed and the battery power is exited, that is the tractive system. So when we say tractive system must be active, you can also think of that as like the air's got to be closed. Yeah, so we passed all our startup checks, but wait, there's one more thing we need to do. And to do that, we're going to chat about the motor controller. All right, so the motor controller, it's got some capacitance in it. I don't know if it's actually like discrete capacitors or if it's just like internal capacitance of the components, but either way, it has some amount of capacitance in it. 440 microfarads worth of capacitance to be exact. So if you look at that, go back to this diagram, I'm going to take away a few parts of it. So just look at our HV system. So this is the motor controller right here, right? it's wired in series with all these other elements, and it's got this amount of capacitance inside it. And if we look at the equation for current over a capacitor, right, it's equal to C capacitance over change in voltage times change in time. And if we try and calculate that, right, that means our current is 440 microfarads times change in voltage. So our battery is 400 volts, right? So it's 400 volts from nothing over a very, 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 very small amount of time, like literally just air closed, boom, 400 volts, right? So if you work this equation out, that's a lot of current, right? A very, very large amount of current. If we go back to our diagram, you can think of like when you first connect a capacitor in series in a circuit and the capacitor is fully discharged, that capacitor is essentially like a wire, right? It's got very, very little impedance, which is sort of like resistance, but for capacitors. So if this circuit's got very, very low impedance, then again, you can look at Ohm's law and say, okay, well, the current must be super high then. And the problem with that is we've got some of these other components in series in here. We've got the airs. And if you look at the data sheet for the airs, they're rated for some amount of maximum current. And the exact amount is like not really super important, but if we've got all this like super high current flowing through every single time we turn on the car, that can potentially damage some of these components. And for the airs, especially in an extreme case, right? If you can put so much current through the airs that it'll actually heat up enough to slightly melt and weld the two contacts of the relay shut. And that's very, very bad because later on, if we want to open the shutdown circuit and the air is welded shut, we can't open the shutdown circuit. We can't turn off the car, which is another very unsafe situation to be in, right? So how do we do that? How do we lower the amount of current flowing through a circuit? You add a resistor. In this case, we had this pre-charge resistor, and we connect it up with a big chunky relay. And so now what will happen is when we first go to turn on the car, instead of immediately closing this air, we'll actually close this pre-charge relay first. And so the current has to pass through this resistor, and then we can slowly charge up the capacitance in the motor controller. And once it's all charged up, we then open this relay and close the air, and we can get to driving. Cool. So now we've gone through every single step. Throttle is talking to the throttle, brakes coming in, dashboard coming in, goes to the motor controller, goes to the motor, which is getting its high voltage. We're doing our pre-charge, and we're moving. I'm going to skip this quiz in the interest of time. And now we're driving, right? Everything I've gone through, all of those things need to happen in order for our car to drive. Okay. We won endurance. We were awesome. Now let's stop. Wait, we forgot about all that capacitance that was left over in the motor controller, right? If you look here, let's say, we pulled out the HVD because we want to stop, right? So these airs are going to be open, right? No current is passing through, which I've visualized by sort of, the laser pointer went away, I just realized, which we visualized by breaking this circuit here and here. But those capacitors in here are still charged up. There's still 400 volts sitting in those capacitors. And we need to figure out a way to dissipate that. So the way we do that is with another discharge relay and discharge resistor. So when we open the shutdown circuit, this relay will actually get closed and will complete this circuit here. And the current, you can almost think of it as like a cool down lap. It'll just go through here and dissipate its energy over this particular resistor. And then and that will basically allow us to discharge that capacitance slowly. And you might be asking yourself, okay, well, how does the discharge relay know when to close and when to open? Like, is it connected to the shutdown circuit? And the answer is yes, it is connected to the shutdown circuit. And this relay is something called normally closed. So if you think about like most switches, they start out like not connected, like open, and then when you power them, they'll connect. The discharge relay is actually the other way around. So it starts off closed, and then we power it, it switches to open. And the discharge relay is connected to the shutdown circuit itself. So if you think about it, When the shutdown circuit is off, when there's no power going through it, it's closed because the relay is not being powered. This is exactly what we want, because when we turn off the shutdown circuit, we want the discharge relay to be closed. But when we open the shutdown circuit, sorry, when we close the shutdown circuit, when we fully power it, this relay is getting powered, and so it will open. Which means that when we're actually trying to drive, we don't have current going through this path here. That would be counterintuitive, or counterproductive, I should say. Cool. So how does a discharge circuit know when to open?
While we're stewing on this question, can I ask how the recharge relay is controlled? Is that software?
Yes,
Or is
so
it
that
like-
is controlled by the air control board.
The
Great
air
question.
and so the pre-charge has to open before the air opens, right? The
Yes.
pre-charge
So,
relay.
yeah.
So
So
how does the timing work?
yeah, great question. So the way that sequence of events happens is the air control board notices when the shutdown circuit is closed. And it'll be like,
Okay.
yeah, okay, all the shutdown circuits closed. Then it closes the pre-charge relay. And then it waits until the motor controller voltage matches the battery voltage. So the motor controller is always telling us its voltage over CAN. So we wait till the motor controller is all charged up to the same as our battery pack. And then once that happens, it opens the pre-charge relay and closes the air, one of the airs.
Right.
And that's all
Is
done.
that- So is that like all the other steps into this point have kind of been like there hasn't been like firmware directly in the path of closing anything, but sounds like there is firmware right here. Is that accurate?
Yes.
Or like even can like
There are other ones like the BMS deciding when to open and close the shutdown circuit. That's done in code as well.
oh that's fair. Okay, that's true.
There might be a few others that I'm trying to think of. But yeah, in this case specifically, yeah, the pre-charge is controlled by software.
But and you're saying discharge is not though, that's totally passive.
Discharge is not, that's correct.
And so is there any concern that like in that switching, there will be a brief like moment where the discharge relay is closed while current is, I don't know, like could we ever burn out the discharge resistor? Or is it designed such that that can never happen?
It would be very difficult because if you think about it, the discharge resistor is designed to operate at 400 volts. It's designed to be able to take that full amount of voltage in the motor controller and be able to dissipate it. So it would probably be very difficult to burn out that component. And there might be some rule that says it's got to be rated for our max current and max voltage as well.
The particular resistors that we use are rated for like 100 watts of continuous power.
Yeah.
Wow. Wait a minute, that's like a big resistor.
So power equals current times voltage in this case. So if you got 400 volts, that would be what, 250 milliamps of continuous current.
But do they look like big or are they just like service mount parts somewhere?
The resistors
some-
themselves are not massive, but we do have these big chunky heat sinks attached to them.
Oh, okay. So like they're very visible in the car, I presume, like in the service section.
Yeah, they're on there's a board actually called the pre-charge discharge board that has both of these
Okay.
resistors on it.
Oh, okay. Cool.
Okay, I know I'm a little bit over time right here, so if you need to leave, feel free. We are like super close to wrapping up though. Okay, so that's how Mark 6 goes. That is basically everything at a high level that is necessary to make Mark 6 go. So I'm gonna do one final recap. So we start with our block diagram, right? Nothing's on right here, so nothing's connected. We flip the GLVMS, right? And that turns on the grounded low voltage system, which starts immediately sends power to all of our LV boards. At the same time, the CAN bus will come online, and all these boards start talking to each other, sending all kinds of information over CAN. Along with that, you got some other forms of communication, miscellaneous, that come online, and the shutdown circuit will also come online. And the shutdown circuit, again, is stopping at all these different nodes. So you can see how, right, like this is depicted as kind of a bus in this particular block diagram when it's really more of like a straight line. So let's say all of our shutdown nodes are good. We flick the TSMS, which is the final node in the shutdown circuit, and that allows the airs to close. And let's say we complete pre-charge and all that. And that allows high voltage to flow through our motor controller and our motor. Right? But we're not ready to drive yet. The dashboard's got to check for that. So the dashboard is checking, are we in our tracking system active, right? Are the brakes pressed? Is the start button pressed? Once the dashboard says A-OK, now we can start hitting the throttle pedal, which is what APPS means. And we can start moving. And I have a really quick video I want to show you guys of one of the times that we spun the wheels on Mark V. And I've put it side by side with a dashboard of our CAN messages. So you'll actually be able to see every single one of these steps happening in real time. Now, quick disclaimer, in this video, you will see people spinning wheels inside the LPB. We should not be doing this. We should not have done that, and we should not do it at any point in the future. They had fire extinguishers, and they were spinning at low speeds, but it is still unsafe. So we should not do this in the future. But with that disclaimer out of the way, I don't know if Zoom is going to like actually really show this video very well, but I'll try and pause at the key points. And you can also go back and watch this video as well. So.
Really? Oh, maybe I should change the location.
Okay, so right here, this is the first point I'm going to pause. So what Jack just did was flip the track the system master switch. Right, and when you do that, you can see that on the left here, all of the shutdown nodes are now reading as closed. And one of the airs is also reading as closed. The other one is open because we're still in pre-charge, as you can see right here. So we're in pre-charge. The next thing that's going to happen right after I press play is pre-charge is going to finish and the other air will close. And you'll actually, if you listen closely, you'll be able to hear it. You'll be able to hear that relay flicking. So I'll go ahead and press play. Okay, so the next thing that's happening right here, I didn't quite pause in time, but it's okay. So Elvis is leaning back and hitting the brakes right here. It's reading brake light off because I didn't pause it in time. And then Jack over here is hitting the start button. This is Jack, by the way. He's the tank top guy. I realize not everyone might know him. So Jack is over here hitting the start button in the cockpit. And as soon as he does that, right, our tractor system is active, as you can see in the air control status. So this keeps turning off on me. Track system is active, as you can see in the air control status. And once Jack hits the button, you can see in the middle table that we are now ready to drive. And that buzzer that you heard is the ready to drive buzzer. And so that'll sound whenever we're ready to drive. So after that happens, then we'll hit the throttle pedal and you'll see us move forward. Oh, that's not what I meant to do. You can see here, we're in the throttle position. You'll be able to see that move up, and you'll be able to see the actual torque request down here as well.
But is someone like manually fiddling with the pedals in that video, or what's the deal?
Yeah. So if we go back here, Yeah, Jack is over here pushing the pedal with his right hand.
Okay.
Really?
Okay. So one final note that I have for you guys. You might be thinking like, whoa, that's a lot of super complex features, right? To ensure the safety. Where did you guys come up with everything? And the answer is the rules. I would say like above 90% of our design decisions are all informed by the rules. The shutdown circuit comes from the rules. All those rules about the throttle and having the different potentiometers, BSPD, all that comes straight from the rules. So if you ever have like a question, the single source, of course, like you can always ask anyone on the team, but the single source of truth will always be the rules. And if you really want to get the final word on something, nothing else is a substitute. Not old rules, not senior engineers, not me, right? The rules are always the final say. Cool. With that, gonna have a couple of minutes here for any final questions. I also want to give a really, really big thank you to Adi Sudhakar, who's an alum from the team, who gave an original version of this presentation for an earlier car, and who I also stole a bunch of graphics from.
A question about the brake pressure sensor.
Yes.
Is that the over travel sensor or is that a separate sensor?
No, that is something different. So see if I can find a little slide here. So the bots, here we go. So the bots is literally just this like little light switch looking thing. Whereas the brake pressure sensor is somewhere else along the actual like hydraulic brake line, measuring the pressure. So they're two different things.
Okay.
Do we have two sensors for the left, for the front and rear brakes, or is it just like one?
Sorry, could you repeat that one more time?
Like we have two separate, like, hydraulic lines for the front and rear. Are we measuring both of those or just one of those?
Are they like entirely separate?
Yeah, I think so. That's how you get redundancy for braking.
I
Also, I've
see.
never seen this sensor. I will admit,
Yeah, me neither.
Does it exist?
To the best of my knowledge, we only have one brake pressure sensor, actually. Maybe we do have two and I don't know about it.
I mean, like,
Something to look into.
it's
I don't
like,
think we
is it
put
a
it on
blue-
Mark 6 just yet. In Mark 5, I know it wasn't like in the pedal tray. It was somewhere closer to the back.
Okay, interesting. I mean, this is. The pressure switch is only for arming, is for like turning on the car, right? It's not getting checked while you're driving. It's
No,
only
the brake
just
pressure
set-
sensor is how we check if the car is braking for everything. It's how we turn on the brake light.
really?
It's how we check BSPD.
But somehow we're only checking one of.
For as far as
Okay,
I know,
that's
we've
interesting.
always had one pressure sensor.
Okay, interesting. I'll maybe drop a little message in the cockpit channel to see what people know about that.
Yeah,
if it's
that'd be a
something
good thing to
integrated
find
yet.
out.
Is it something that connects to like a harness, or is there an actual board?
No, it's not connected to a. I mean, it's connected to a board, but it's not like on a board. It's connected
Okay.
via wire.
Interesting. Do you know who's like responsible for this part?
I'm not sure, but I can find out.
To keep it on the radar. Yeah.
Cool. I'll hang around for a few more minutes in case anyone has any questions. But if not, thank you all so much for coming. I hope this was helpful in one way or another. Yeah, hopefully you'll have a little bit more confidence when you're working around the LPV. Also gonna cut off the
Awesome,
recording
thank-
here.
Thanks, Amit. This is